So this chapter is all about gravitation, something I like to call Newton's fourth law. Newton's fourth law tells us that the force due to gravity anywhere in the universe is equal to a big G, which is the universal gravitational constant, times a mass 1 times another mass 2, all divided by r squared. And what this does is it allows me to calculate the attractive force due to gravity between two masses, mass 1 and mass 2, based on the distances between those two masses, which we call r. The gravitational force is attractive between masses, so that means that all mass attracts all other mass in the universe, and you can calculate it if you know your two masses, mass 1 and mass 2. And we usually treat gravitational bodies as spheres with all of their mass concentrated at their center. So this is a concept way back from chapter 1 known as a point particle. So we treat all the masses in our problems typically as point particles, where all the mass is right at the middle of a sphere. Before we get too far along, I recommend you try out Checkup 9.1 to make sure you understand gravity. And as we continue onward, we'll talk about gravity in the case of circular orbits. The most common type of circular orbit we like to talk about in physics, and in particular since I'm an astronomer, we'll go with the solar system. So we have the sun at the middle of our solar system. It has a particular mass. We'll call it mass of the sun. And the Earth orbits around this sun, the heliocentric view of orbits. Earth orbits, and it orbits due to gravity. So it has a specific distance that I am from the sun, 93 million miles. And we have a specific mass of the Earth. And I can calculate the gravitational force that keeps Earth in orbit using this equation. The gravitational force is equal to G. This is big G, the universal gravitational constant. Take note that big G is not the same as little g. So this is not 9.8. It's a number you go and look up in a table. So big G times the mass of the sun times the mass of the Earth, all divided by their separation squared. So I can calculate the force due to gravity between the sun and the Earth. Now can I calculate how fast does the Earth move around the sun? How fast is this orbit? So if I want to draw where the force due to gravity between the Earth and the sun acts, the force due to gravity is attractive, always attractive, so it pulls my Earth towards my sun. This is the gravity from the sun acting on the Earth. So how fast is this orbit? We can see that the force due to gravity of the sun on the Earth, it acts towards the center of a circle. So this means it's a centripetal force. So if it's a centripetal force, I can take that force, G, mass of the sun, times mass of the Earth, divided by r squared, and set it equal to a centripetal force, which is mv squared over r. I can do some algebra. I can solve for my velocity v. My velocity due to orbit is then going to be the square root of g times the mass of the sun over r. And I found the velocity of an orbit, the speed of an orbit, due to the force of gravity between two objects, in this case the Sun and the Earth. And all it depends on is the separation of the two objects and the mass that's actually pulling your second object in. So now that I know the speed of an orbit, what if I want to know how long an orbit takes? Usually we describe this with the letter T, and T is equal to the period. How long the orbit actually takes. I can take my velocity v and set it equal to 2 times pi times r. This is the circumference of a circle, the distance that my orbit will be since it's a circle, divided by the time that it takes. This is just the definition of velocity. It's a distance divided by a time. The very definition of velocity from way back a couple chapters ago. So this tells me that 2 pi r over t, my velocity, written in terms of period, is equal to the square root of g times ms over r. And usually we don't like working with square roots, so I'm going to square both sides of this. So I'm going to get 4 pi squared r squared divided by t squared is equal to g times the mass of the Sun divided by r. And since I don't like fractions, I'm going to try to get rid of my fractions. So I'm going to multiply both sides of this by r and both sides by t squared. So that's just going to get rid of my fractions. My fractions are going to cancel out. My r's will cancel out on the right. My t squareds will cancel out on the left. So I'm left with 4 pi squared r cubed is equal to g times m Sun, mass of the Sun, times period squared. Four pi squared and gms, these are both constants. So the real thing to point out here is that the cube of the distance cube of the separation between your orbiting bodies is proportional to the period that they take to orbit squared. And this fact, the cube of the distance being proportional to the period squared, is something we'll encounter a little bit later on with a man named Kepler. So as I just mentioned, we'll encounter t squared, period squared, equal to distance cubed with a man named Kepler who has 3 laws of motion. His 3 laws describe how real orbits actually work. These laws are empirical, so they were determined based entirely on data. He didn't know why they were true, he just knew that they were because they matched the data that he had. Kepler's first law tells us that planets orbit in ellipses, where an ellipse is just a flattened circle. We'll talk a little bit more about ellipses in a moment. With the Sun at one focus. To understand what that means, we need to look at some geometry of an ellipse. So an ellipse is just a circle that's kind of been flattened out. And you can draw 2 focus points. You can find your ellipse, you can draw your ellipse based on where these 2 focus points are. We'll see an example of that in class. But this is what the orbit of a planet looks like. Not an exact circle. It has this kind of flattened circle shape. We have these two focus points that allow us to draw our ellipse. Again, we'll see that in class. And we put the sun at one of these focus points. So that's Kepler's first law. Planets orbit in ellipses with the sun at one focus. Kepler's second law tells us how fast planets actually orbit. It tells us that planets sweep out equal areas in equal times. This is another one that's kind of hard to visualize, kind of hard to see without actually drawing it or watching a video, watching an animation of it. So we'll do that in class as well to help understand why planets sweep out equal areas in equal times. Then a consequence of this is Kepler's third law, which we've already seen, which we've derived from Newton's laws, is that the period squared is proportional to the distance cubed. And for an elliptical orbit, the distance is going to be this letter A. So T is the period, and A is the distance. And for an ellipse, this quantity A has a specific name. It's called the semi-major axis. So to really understand Kepler's three laws, let's look at a little bit of geometry of ellipses so we can understand what Kepler's laws are actually telling us. Review Kepler's first law. Planets orbit in ellipses with the sun at one focus. So I can use focus points to draw an ellipse. We'll show you how that works in lecture. But if I draw my ellipse, I have my two focus points. And I can draw a line that's directly across the widest part of this ellipse. This line is called the major axis. But we don't typically use the major axis for ellipses. We use half of that distance, half of the longest point, longest distance across your ellipse, and we call that the semi-major axis, and we label that with an A. So this is the distance that we're talking about in Kepler's laws. A is the semi-major axis. It's a way to describe how large your orbit is, how large your ellipse is. Semi-major axis. If we recall Kepler's first law, the sun is at one focus point. So if I put the sun here, what we find are there are places in orbits that have specific names. We have the place that's closest to the sun. That's going to be what we call perihelion. And we have a place where the Earth is farthest from the sun. We're going to call that aphelion. And finally, the last part of the ellipse that we want to label is going to be at the halfway point. We draw a vertical line that describes the height of your ellipse, and this is going to be something called the minor axis. And the proportion between the size of this semi-major axis, this horizontal part, and the minor axis, the vertical part of your ellipse, is something called the eccentricity. And that describes We describe it with an E. A lowercase e is the eccentricity, and this describes how flat your circle is. So we'll watch a video about this as well, but we'll try to explain it now. Equal areas in equal times. Kepler's second law. What I do to figure this out, to find Kepler's second law, is I imagine my sun at one focus point, and I imagine I have a planet over here near perihelion, near the closest approach to the sun. And I imagine taking a line and drawing it from the sun out to my planet. And I imagine I do this at a time t1. Then at a slightly later time, after the planet's moved around in its orbit a little bit, we'll call that time t2. I again draw my imaginary line. And I can think about my planet and imagine that it's traced out some amount of empty space during this time. Some area has been swept out by that planet between time t1 and t2. And I'm going to call that area 1. Then I think about my planet at aphelion, after it's farther away. I draw my imaginary line at some time t3. And then I imagine drawing my imaginary line at some later time. We'll call it t4. And I again have swept out some certain amount of empty space, some certain area, by drawing that line. My planet is sweeping out an area. I'm going to call that area 2. And what Kepler's second law tells us is that if t2 minus t1, the time that it takes for this first area to be swept out, is equal to t4 minus t3, the time that it takes for this second area to be swept out, then I know that area 1 is equal to area 2. So the planet has swept out an equal area in an equal amount of time. And this has a consequence that close planets move fast, and far planets are slow. But does this make sense with Kepler's third law? Kepler's third law tells us that period squared, the time it takes to orbit, is proportional to the semi-major axis cubed, to a big distance. So if A is big, that means T has to be big. So a far orbit leads to a long time orbit. To have a long time orbit, your planet has to be moving slower. And conversely, if the distance is little, if you are close, then the period is also little. You have a short time for your orbit, so you have to be moving faster. So Kepler's second and Kepler's third laws really result in the same conclusions. Close planets move fast and far planets move slow. So one of the most interesting aspects of Kepler's laws, which involve these elliptical orbits, is you can take a portion of that ellipse, just a portion of the orbit, and you get a shape that we're very familiar with already. This looks a lot like a projectile. A projectile is really just an incomplete elliptical orbit. So you can use Kepler's laws for projectiles. They're just incomplete elliptical orbits. And finally, one of the most practical aspects of orbits is figuring out what the energy of orbits is. This is very useful and very necessary for making sure that our satellites stay where they're supposed to be. They have to have enough energy to overcome the force of gravity that would pull them down. So let's say I have my Earth sitting here, it has a specific mass, and I have a satellite that starts to fall from a position P1 at a distance R1, and I need to raise it up to a distance P2 where it will no longer be falling. In order to do this, I have to perform some work. The work I have to perform is the integral from P1 to P2 of the force that it takes to raise me up the distance that I need to go. So the force that this object is feeling is equal to negative g times m times the mass of whatever I'm trying to raise up divided by the separation of the two objects squared. So this is my force. So I can calculate the work that's required to raise this orbit up. Work is equal to negative integral from R1 to R2 of g m, the two masses, over r squared, dr. So this is the definition of work from a force. So I'm calculating the work required to raise this orbit up as a result of the gravitational force between two objects. So I can rewrite this a little bit differently. I can rewrite it as work is equal to negative g times m, where I just pull all those variables outside of my integral since they're constants, from two positions r1 to r2, and I'm just going to rewrite this 1 over r squared as r to the negative 2 times dr, so that I can use my power rule involving n equal to negative 2 in this case. So here's my integral that I need to solve. I use my general formula for integrating a power. I get negative g times m. I take my r, I raise it to the negative n plus to the n plus 1. So negative 2 plus 1 gives me negative 1. I divide by n plus 1. Negative 2 plus 1 is again negative 1. And I evaluate that at two positions r1 and r2. So here my two negatives are going to cancel each other out, and I'm going to find that my work is equal to g m over r2 minus g m over r1. So this is the work that's required to change my orbits. So I can see that my orbital energy, my orbital gravitational energy, U, is going to be equal to negative g times m divided by r. And I got this by finding the work required to change the orbit of some object. And something to note is that orbital gravitational energy is always negative. which is a consequence of the force due to gravity always being attractive. So the final point to make is that the total energy of an orbit is going to come from two different types of energies. I can have the total energy equal to K plus U, which is going to be equal to 1/2 mass times velocity squared, the kinetic energy, plus the gravitational energy from being in orbit, which is negative G m times m divided by r. So the total energy of an orbit is 1/2 mass times velocity squared plus a negative gmm over r, where again this negative is a consequence of the force being attractive for gravity.